This lecture is on polyatomic ions, writing their Lewis dot diagrams, and naming the types of salt compounds they make using the names from Table E, which I call the what the heck is that table, that cluster of nonmetals. Notice this is selected polyatomic ions. There are more, but these are the most common, and there's only a finite number of them. And you don't have to memorize them, you just have to know where to go to use them. In other courses, because some of the commonality of some of these ions, like a nitrate ion or hydroxide or phosphate, you'd come to know them by just using them. So in any case, let's do a Lewis dot diagram of one, and then we'll talk about its hybridization. We'll go into all of the details and introduce a concept, something called resonance, along with some formal charges and some naming. So a lot going on here that I'm trying to introduce. So let's start with the naming of, the nitrate ion, like I did in class. So if I ever asked you to write the Lewis dot diagram of a polyatomic ion, you would notice it has a charge. So the first we'll deal with is NO3 minus. Now I did this, of course, in class, and I want to do it again, just to make sure we understand what's going on. I have the N in the middle, and I have my 3 O's. And what I'm going to do is I'm going to put out the valence electrons. 1, 2, 3, 4, and 5. And I could put them any old way, but I'm trying to make sure that nitrogen somehow has its 8. This oxygen has 1, 2, 3, 4, 5, 6 valence electrons, and you can notice by sharing the nitrogen and the oxygen have the 8. And let's say this oxygen, let's put a double bond here, and you'll see why I need to. Okay, and the reason I put a double bond, so if I want a single bond here, I wouldn't have enough electrons for the nitrogen. See, nitrogen needs 8. It's 1, 2, 3, 4, 5, 6, 7. All right, let me show you what I mean by that. And I don't want to go too fast. So if I take some away, if I was to do the same thing and put all lone pairs and make one bond, and if I did the same thing over here, 1, 2, 3, 4, 5, and 6, you would see that nitrogen, well, if I was to get another electron, because this means that I'm going to gain an electron, let's put that electron here, we'd only have 6. Okay, so we need to have a double bond. The oxygens are happy, but the nitrogen only has 6, so what I do is make a double bond happen. And formal charges, when we get to that, really help us understand this a little better. But in any case, put this here, and my lone pairs here. And now you can see clearly that this has 8 electrons. And this, of course, right here is the one I added to make all this work. Without this one extra electron, this wouldn't have its 8, the nitrogen, and the oxygen wouldn't have its 8 by sharing. Okay, so this is a stable cluster of nonmetals that by gaining an electron, now I write brackets to show that this entire cluster or polyatomic ion is -1. Okay, and that is how we would do it. Now if I had phosphate ion, PO4 -3, as given to me in the reference table, okay, so if I was to get rid of this and go back to my what the heck is that table, there's my phosphate ion right here, front and center. You could see that I would draw the P and the 4 O's, and I would add 3 electrons to make all this work. And that's how most of these work. Now if you notice, these are clusters of nonmetals, and these clusters of nonmetals would in fact attract a positive, and you can make something called an ionic compound, not this. Okay, so let's go back to where I was working, and let's look at, well, where did it get this lone electron from? Well, let's pretend that I'm a princess. No, let's pretend that there's a sodium here, and this sodium had that valence electron. It had to get it from somewhere, and probably got it from a place that loses electrons easily, and that's what metals do. Okay, to have stable octets, or in this case a stable field electron energy level, valence shell, okay, because it's 1s2, 2s2, 2p6, 3s1. By losing its electron, it has 2 filled energy levels as stable as argon. Okay, any case, so this electron was transferred, as you guys have learned, and by transferring and sodium completely losing it, we're not sharing here, this sodium becomes +1. What we have is an ionic bond between the ions, and the name of this is sodium nitrate. The naming is not sodium oxide or nitride. Anytime we have a polyatomic ion, anytime we have this what the heck is that cluster that we get from table E, it's the name of that cluster. And because this is a salt or an ionic compound, we could care less about how many in the crystal. We know it's a 1-to-1. And we figure out that empirical lowest whole number ratio by making sure how many of these do we need to make the overall formula, the empirical formula, okay, the lowest whole number. So this is NaNO3, and it'll be a solid because it's a crystal, it's anionic. But what you need to understand is that this is an ionic bond between the ions. Some teachers teach that ionic bonds are metals and nonmetals. Well, and honestly, the best way to think about an ionic bond is a bond between charges, all right? And of course, the bonds in between the nonmetals here, okay, oops, there's no bond there. All right, so the bonds between the nonmetals here are covalent because they're forced to share because the electronegativity difference is so similar and very high. So we have covalent bonds and ionic bonds, and anytime you have a compound, a salt, an ionic compound that has a polyatomic ion or cluster that we get from table E, or what the heck is that, or from knowledge, we know that there is an ionic bond between the ions, and then there's a covalent bond between the nonmetals. So this is the only chemical structure, really, that you're going to see that has both ionic and covalent bonds in them. Okay, now let's go name some of these. Before we do that, we go back to our tables that I gave you a little while back. I want to talk about some that are positive. So let's go back to some positive ones. And if you notice, it's easy to understand that we would gain electrons to make these guys work, like my example, but you'll see some ones that are positive. So these are some positive polyatomic ions. Now, they don't lose electrons typically, but let me show you how, let's say, H3O plus or NH4 plus work. This is more of an AP one to explain, but I'll explain these two right here. So let's go do that. So let's do H3O plus. H3O plus, okay, has an oxygen, okay, and it has 6 valence electrons. It's going to bond with 3, so it's kind of hard to work for it this way, but I'm going to show you how it actually happens. So water is what we start with, because essentially what happens is water becomes H3O plus by gaining a proton, and I'm going to show you what I mean by that. Here's water, and here's its one bond with hydrogen, and here's its other bond with hydrogen. Just showing you the X that belongs to the H, doesn't really matter, but in any case, you guys know it's sp3 hybridized. It's 4 pairs of electrons. It's got that bent shape, makes it very polar. Now what can happen is, because it's got these 2 lone pairs, it's very attracted to things that don't have any electrons. Case in point, in our chemistry, especially aqueous environment, we have things called protons, which are hydrogen plus ions. I don't like that color. Hydrogen plus ions are tough to, we don't usually talk to them about that. So we have H plus ions. Now if you notice, hydrogen atom, it has these symbols. It has one what? Proton, and has 1 electron if it's an atom, has 1 minus 1, no neutrons, right? So what you have for hydrogen is 1 proton, and you've got an electron flying around electron dot diagram, or flying around electron cloud model here in quantum mechanics. Or it's a 1s electron, however you want to think about it. Now, when it loses an electron, it becomes H+. When you lose an electron, what's just left? Just the proton. So an H+ is also called a proton. So an H+ doesn't have an electron and is very highly attracted to negatives. Now why? Well, protons are very tiny. They're tiny in their +1. So they're like electron-seeking missiles for things, that places anyway, that where electrons exist. So these guys really attack and find and love these pair of electrons. So this proton attached is just really an H+, and what you have is you have an H+, okay, that attacks or attaches itself to the lone pair. So if we draw this in a more flat way to draw it, so you have a O with a lone pair, it's got its H's here, then you can put an H here. An H attacks, and now you have your H there. And if you notice something, H did not bring any electrons to the table. Kind of like a guy showing up to the party or a gal showing up to the party with nothing in their hand. When you go to someone's house, you're supposed to bring something. Okay, don't be that person that brings nothing to a party. Don't be that guy. Any case, so guess what? H plus was that guy. He had no electrons and he showed up with nothing and he ate the food or used their electrons. So my friends in chemistry, what we have here is something that brought no electrons. But what did it bring? Didn't it really bring a proton? So it didn't bring any electrons. It didn't have to bond with these two. Remember, hydrogen wants to feel like it has 2. And oxygen wants to feel like it has 8. So it doesn't need to, all right, bring any electrons if there's a pair there. So we call this type of bonding arrangement when you're that guy and you bring nothing to the party and you use someone else's electrons that are just sitting there, we call it a coordinate covalent bond. Coordinate covalent bond. Now, it's the same as any other polar bond, right? H and O have 2 different electronegativities. Electrons will be kind of pushed that way a little bit. Okay, it's a polar bond. This would be the negative part of the bond, the positive part. So it's the same thing. It's just that it's how it's made. And how do you know you have coordinate covalent bonds? Well, in order to have a coordinate covalent bond, you must have a lone pair. And in order to know that a coordinate covalent bond exists, you'd have to do the X's and dots. What I mean by that is, if I said to you which of the following structures has a coordinate covalent bond, you would have to see something like this. It has to be clear whose electrons are whose. Notice the X's represent electrons from the hydrogen, the circle dots that are red are electrons from the oxygen. So clearly there's no blue X here, so this is where there is the coordinate covalent bond. Okay, here this is not a coordinate covalent bond. However, once they bond, they're all the same bond energies. So in order to be able to have a coordinate covalent bond, you need to have lone pairs. And again, in order to identify, you have to look at a Lewis dot structure that has different designation of whose electrons are whose, but a very simple thing. Okay, case in point, we have ammonia. Ammonia has 1, 2, 3, 4, 5 valence electrons. H's come by, okay, and give a pair, give a single. And you notice nitrogen has its 8, each hydrogen has its 2, and you've got yourself the ammonia molecule. Well, same thing, an H plus in the environment can attach itself here. And when it does, you get, and because there's a lone pair, it can coordinate covalent bond, and it makes one. And when it does so, it makes this structure. Now, because it's adding what? Just a proton, this whole thing becomes positive. This whole thing, I should have wrote, is positive now. So these things are positive because they're just adding protons, essentially. I know that you could write the structure and probably take an electron away, and that would work too, I guess. But the way to think about it is these guys are adding protons. So we have some polyatomic ions that are positive in the reference table. And they got positive because they had lone pairs that a proton was able to attach itself to and add a proton to, and it made the whole thing positive. And these are positive. So when you say an ionic compound must be just metal, non-metal, that's not entirely true. I could take a positive polyatomic ion, right? And I could have it attract a negative polyatomic ion. Here's what I mean. Let's take the ammonium ion. And let's take the nitrate ion. What the heck are these things? Well, these things are listed as names. This is called the ammonium ion. This is the nitrate ion. Okay, you already have these values, or you have to memorize these if you're not in my class in this course. In any case, these are 2 different clusters that have charges. This one gained the proton, this one lost an electron. And my friends, this would make the following compound, NH4, NO3. 1 positive, 1 negative. If you notice, the name of this would be ammonium nitrate, the name of the polyatomic ions. And it would be a 1-to-1 if you want to do crisscross because one's positive, 1 negative. And notice, where's the metal? Where's the beef? There's no metal here. So when people say ionic compounds are metals and nonmetals, That's not entirely true, is it? Really ionic compounds are what? Attractions between a positive and a negative ion. Sometimes the ions, negative ions, could be clusters and polyatomic, and sometimes the positive one could be a polyatomic. So what are all the combinations to be ionic? Well, definitely metal and nonmetal. Let's go through a couple of them. So we can do metal and nonmetal, like sodium and chloride. We've already done those. Then we can go metal and polyatomic ion. Just like, let's say, sodium nitrate. What the heck is that? Then we can actually go what? Polyatomic and polyatomic, like NH4 plus and NO3 minus. So these are all your arrangements. Actually, there's actually one more. If I have a positive poly, like ammonium, so I can actually have polyatomic and nonmetal. So I can have ammonium, which I know is +1, and I can hook it up with a chloride, -1. And these are all ionic compounds, or salts. They make crystals. They have high melting points. Okay, their formulas are lowest ratios. And they, of course, are electrolytes when they dissolve in water or melted. Now, when you deal with these, you're going to have to deal with something special. And that is parentheses if you need more than one. Case in point. Let's watch very carefully as we name these guys. Let's say I have the phosphate ion. And again, you don't have to know this one yet. That's table E tells you that this, what the heck is this? It's the phosphate ion. Now this phosphate is -3. Well, what if it attracts a magnesium ion, which we know is an alkaline earth that's +2. This is magnesium. What's the naming system, the IUPAC naming system? Well, it's going to be magnesium phosphate. It's the name of the metal. Now, when it was binary, like when it was MgP, this case it'd be this, it was magnesium phosphide. It was IDE ending to say that this was binary, just 2 elements. But when it's ternary, when there's a group of them, guess what? You will use just the name of the polyatomic ion. So magnesium phosphate. So it makes it very simple. But just like here, when magnesium was +2, when we did this last week, when magnesium was +2 and phosphorus likes to be -3, you can crisscross or see the common factor is 6. You need 2 of these for 3 of these to make a neutral compound. Okay, well, we put 2 phosphorus, but here we need 2 phosphates. So if you want to do the crisscross method, clearly we need 2 phosphates for 3 magnesiums. And how do you show that? Well, you show it like this: magnesium, phosphate, and of course you need the parentheses to show that you need 2 of these. So if you need more than 1 cluster. Now why does this work? Because in the crystal, I'm sorry, we're not done yet. Oops, sorry. So you need 2 of these, and of course you need 3 magnesiums. Okay, so we didn't need that for binary because we just had a single element, but this means we needed what? 2 of these clusters. We need 3 magnesium +2s all together. That's the lowest whole number ratio. If you crisscross, reduce the lowest terms, and you need 2 phosphates. And all of this collectively equals 0. But because you need 2 of them, all right? If you find the hydroxide ion is an OH minus. Okay, and where the heck is that? A hydroxide. What the heck is a hydroxide? Well, look at that. Look where you're looking. Hydroxide right there. OH minus. All right, so let's say I want to make calcium hydroxide. Well, calcium hydroxide is calcium. It's +2. Hydroxide's -1 individually. So clearly I need 2 hydroxides for 1 calcium to name this. This would be wrong. CaOH2. If you just do that, your teacher, professor, employer, whatever, this is wrong. It's not 2 H's to 1 O. This cluster is -1. You need 2 of them. To show that, you've got to put the parentheses. Okay? So what I want us to do now is take out those naming sheets that we saw and worked on last week, or the beginning or the end of last week. Okay? And I'll show you what I'm talking about. Okay, here's what they look like. And here's what we named them. Because they were binary, we took the positive element first, like magnesium. And because it was binary, the chlorine became chloride. Now, careful. As you remembered, we used something called the stock system here. When we had things that had more than one charge, like iron, you learn that can become what? +2 or +3. We have to tell which one it is. So FeBr we found to be +3 in this case, because if you've got one Fe +3 and you've got one Br -1, you need 3 of them. So this is going to be, okay, iron, Roman numeral 3 bromide. So if you have a scenario like we just talked about last week, don't forget the ones that have multiples, and normally those are the transitionals, but you're going to learn them by doing many of them. Like look at PbS2. The first one's positive, the second one's negative. Sulfur is going to be -2, -4 overall. They're going to be 0. Okay, so +4. And this is going to be +4 individually. And we would call this lead, because it's +4, Roman numeral 4 sulfide. Now I have a lecture on naming these, but I just want to get to what we're talking about today, which is naming the polyatomics. Very simple. And the polyatomics, or the ternary compounds, look at this. Lead 4 sulfate. Well, it's screaming to me that lead is +4. Sulfate. What the heck is a sulfate? So I go to the what the heck is that table. And I'm trying to get there. And where the heck is it? There it is. Where's my sulfate? What the heck is a sulfate? There it is. It's SO4 -2. So SO4 -2. For my table, what the heck is that? -2. Crisscross applesauce, reduce the lowest terms, however you want to do it. But I need 2 sulfates for 1 lead, so it's PbSO4. And because I need 2 sulfates, Roman numeral 2. Don't forget the ones that have what? Ooh, tin is +2. So Sn is +2. What the heck is a nitrate? Nitrite, I'm sorry. That's an NO2 -1. So you need 2 of those, and that'd be Sn, NO2, but you need 2 of them. Okay? And that's how you go about doing that. Now, if you're having trouble doing that, the naming is very simple. It's from the polyatomic ion. For instance, if we go the opposite way, let's look at something like this. Number 1, you have KHCO3, although my friend in chemistry, that's potassium. So potassium, it's not going to change that. And what the heck is an HCO3? Well, if you look at table E, what the heck is that? That's a hydrogen carbonate. So potassium hydrogen carbonate. This right here is the name of the polyatomic ion. So these sheets are due Friday. You should get a good start on them, and that's what we're going to do. Now, if you want more detailed work on how to name these, I have some individual lectures on them. But I understand the reason why they're positive and negative, and you should be able to do Lewis dot diagrams from them. Okay? See you later. So in any case, make sure you understand that these are due this week.